Also,
we'll see. If he
also
works on that
normally
board,
test code is available from 8 to 12.
but hopefully
Mr.
we'll work
Mathapula is
on
going
the
to that office to
camera
ensure
again.
that the transport, university transport is available, right? Okay.
Lucas, what's going on, man?
So we're done with, are you ready?
It's recording.
With me. We have done with Thevenin's, right?
Yes, sir.
And we have learned it, right? And if there be any problem on Thevenin which I cannot solve, I'll get back to you and you solve it for me, right? Yes or no? Yes. Big yes or no?
Yes.
Why yes? Yes.
Yes.
Right. So we are going to do Norton's
Make
now.
sure that we don't speak during the lecture. If you
We
want to
have
ask
a
him,
couple
just
of
ask the
more.
puzzle,
We
because
need
otherwise
to
it
cover
interferes with the
two. We
audience.
need to do Norton's theorem. We need to do
No,
started
you two can
conversion.
speak, it's just me and you can't speak.
Maximum
You
order.
guys can speak, it's just
So whatever we have done, what we are going to do, everything will be in your class test as well as in your semester test one. Clear?
Yes, sir.
We are doing in this way so that one preparation can do the both. Meaning, you are preparing for the class test, you are writing it on Thursday. Obviously, you will do some mistakes. You learn from the mistakes so that you do better in the semester test. Does it make any sense?
Yes, sir.
It should be, I think, last week, not next week. Last week of February, Thursday and Friday. You'll get notification on WhatsApp. There?
Yes, sir.
It's for everybody, not a particular group. Okay?
On the group.
Last test? Yes. Yeah. Okay. So we are going for Norton's theorem. So should we do that way we did for the previous one? We do not read this first. We do not read this first. Let's do something what we can probably understand. Okay, let's take a circuit. Don't try to write anything. Let's try to understand how it looks to us. Here also, we need to find out Norton's current in the name of Norton. So this is Norton's theorem. We are going to find out Norton's resistance. What we did in Thevenin's, we did Thevenin's voltage and Thevenin's resistance, right? To get Thevenin's equivalent circuit. Here we will have Norton's current, not voltage, and Norton's resistance to get Norton's equivalent circuit. To find out the final current which will be flowing through the load. Right? I think the best way would be if we go back to the examples we did, might which way am I going? Okay, let's go to the example we did on Thevenin's. Something like that, right?
Yes, sir.
Let's do on that. So what we are going to do, here also there will be step 1 is exactly similar to the Norton Thevenin's theorem. Meaning we are going to find out this resistance, what we did there, this resistance would be now Norton's resistance, not Thevenin's, because we are doing Norton's theorem. Clear?
Yes, sir.
The same process. So we are done with step 1. Step 2, what we did there, we found open circuit voltage here, right?
Yes, sir.
Now here what we are trying to do, we are trying to find out short circuit current. Meaning we are removing the load and we are short circuiting these 2 points.
Okay.
And then we are trying to find out the current flowing through that. That current will be Norton's current. Does it make any sense? So here we can quickly do okay, so whatever resistance you have and all this, you are going to short circuit that one, meaning you will have 2 loops, this loop and that loop. You remember when we did the Thevenin's, this was open circuit, that loop was not there, only we had 1 loop. Clear? Here we have 2 loops, this loop and that loop. We are going to write mesh equation for both the loops. We are going to solve the currents here and there, right? Then we will find out what current is flowing there. Clear? So this is your Norton's current. So we get step 1, Norton's resistance. We get step 2, Norton's current, which is the short circuit current. And then we get some equivalent circuit here. This is not similar to that one. We are going to show how it looks like. It will look like that one. So this one will be, this bit is your equivalent Norton circuit. Meaning you will have Norton resistance here, which is parallel to the current source. This is a constant current, right? Meaning its internal resistance is infinity. Irrespective of any load, that current will remain constant. That's the current source. That current we calculated by short circuiting there. That was the Norton's current. So this is Norton's current, this is Norton's resistance, this is Norton's equivalent. We are going to put the load resistance here. Then we are going to find out the current passing through the load. Clear?
Yes, sir.
So if you have load resistance here, what would be your current passing through that? Meaning this current coming from here, it will be divided into 2. One will go through that, one will go through that.
Yes, sir.
Again, it will go by the rule of parallel division of parallel currents. Right? So this current would be this current times that divided by this plus this. Does it make any sense?
Yes.
So that will be this current. That is the answer.
Okay.
Okay. Should we repeat?
Yes.
Step 1 is exactly similar to
7.
Thevenin's resistance. Step 2, instead of open circuit, we are going to short circuit the load terminals. Removing the load resistance, we are short circuiting. A and B will be short circuited, right? Then we will find out the current passing through the short circuit. Clear? That is your Norton's current. So we get Norton's current, we get Norton's resistance, then we get Norton's equivalent. Then we put our load resistance here, then we find out the current passing through the load. Right? Question? No. So let's quickly do the one we did previously. Probably that will, or should we have different values? Should we have different values? Yes or no? No. Huh? Yeah. You said no. What is that? Where is that? So we are going to keep similar sort of circuit, but we are going to have different values so that we can quickly understand the theorem. We will take it from there. Norton's theorem, let's Let's take problem 1. Okay? Sorry? Is it too much? Looked out. Okay. So now let's put this one say E1, R1, R3, that is not. Sorry. So now get the load resistance here. So this is your RL. Okay? Now without looking at those values, let's put it 10 volt, put it 10 ohm, this one say 20, and this one say 50, and this one say 200. Different values there. Now we need to find out IL by Norton's theorem. Right? Clear?
Yeah.
This is the circuit, and so 50, 20, 50, 10, 20. 200. Okay. Step 1. Step 1. What we are going to do, we are going to find out the Norton's resistance, meaning Rn equal to how much? That is open circuit resistance across the load, when the load is open. Okay? Just to remind you, this one is equivalent to R Thevenin of the previous one. Clear? But we are using the term Rn. The process will remain same. This one will be short circuited. This resistance will be there. This resistance will be there. And also will have this resistance. So we are looking back from here. This one is 10, 20, 50. Clear? So the next step would be, so we need to find out Rn from here. So next step would be these two will be parallel combination, and then you get this one. So that is your 10, and this one 50 times 20 divided by 50 plus 20. Can you see there? Okay, little bit. Okay? So this one is what we are getting from there. Ultimately we are getting one resistance, and that resistance will be Rn. What is that value? This one would be, so tell me what is this value? 100 divided by 7p, right? 10 by 7. Clear? Is it that? Is it 100 or 1000? So 100 by 7. Okay. So 100 by 7 plus this one. Okay? What is that value? Can I look at it? So this one should be 100 divided by 7 plus 10 equal to 24. This one would be 24.286. With that, so we have the open circuit resistance, which is Norton resistance here, which was Thevenin's resistance in the previous case. You done? Go. Huh? Mechatronics, okay. What is the other ones?
Can I just
Okay. So now we are going to step 2. We are going to step 2. We need to find out short circuit current. We say ISC, short circuit current, but we give it a name that is Norton's parent. I Norton equal to how much? Here, in order to do that, the original circuit will be there. Original circuit will be there. Then this one, so this was point A and this was point B. So this one is point A and this one is point B. So we are going to short circuit this one. Meaning it is connected by a wire with that mechanical resistor. Clear? So they are connected without any resistance. Now we need to find out the current passing through that. This current will be IA. Right? We need to find out that. So this one was 10, this is 20, this is 50, and this was plus minus 10. Clear? Now as we say, let's take this one loop, and this one another loop. This one is I2, and this one is I1. Clear? You can see that? Now, so far so clear, right? So we need to write two equation, right? And we remember that voltage drop. If you go along the direction of the current, that is drop, negative. If you go against the direction of the current, that is rise, positive. For a battery, if you go from positive to negative, through the battery, then drop, negative. If you go from negative to positive, rise, positive, right? Okay, so here if we start at this point, so this one would be what? Drop. So we are going to write here, look, in this loop there is 20 and 50, okay? So we are writing 20 plus 50 times I1, it was drop, negative, okay? And there was another current, I2 is going in that direction, clear? Yeah. So that would be 20 I2, positive or negative? Positive. Positive, because we are going against the direction of the current, that is voltage rise, positive, clear? Yes. And then here we going from negative to positive. Voltage rise, that is plus 10. Plus 10 equal to 0, equation 1. Clear? Yes. So quickly we can say 70 I1 negative plus 20 I2 plus 10 equal to 0. Okay? Or we can say 7 I1 plus 2 I2 plus 1 equal to 0. Equation 2, we are going along this one. We start here. We have, when I2 is going to that, the resistance we have 10 and 20 in this room. So 10 plus 20 times I2, but this is drop, right? Negative. But here, there is no voltage. Here, there is a current I1 going this direction, but we are going that direction. So that would be 20 I1 negative. Negative.
Positive.
Positive. Okay. Equal to 0. So what we get? Minus 30 I2 plus 20 I1 equal to 0. So we can say 2 I1
So just move up a bit.
equal to 3 I2, okay? Or we can say I1 equal to 3 by 2 I2, right? So now if we put this value in equation 1, that is we are going to put this value here. So we are going to put this value in this equation. That value is, we got this value here, we are putting this value there. Combining these two, so we are getting minus 7 I1.
No, so it's minus 7, 3 over Antik
Just 70.
Minus 7?
Just 7.
we must
Okay, no, sorry, we are going to use I2, right, sorry.
Yeah.
So it would be, so let, so minus 7 times 3 by 2 times I2, right? Plus 2I2 equal to minus 1. Okay? Now what is the value? So it would be I2 times 2 minus 21 by 2 equal to minus 1. So I2 equal to how much? Can I add that? So 21 by 2 minus 2. So it should be 2 by 17, is it that? 2 by 17. The answer should be 0.118.
8.
Okay, let's put it 0.118 ampere. And this one is your Norton current. Yes? So we got Norton current. We got, when the display is kind of something happening again. It's not moving, but it is. What is happening? Did I kill it? So we got, okay, let's do it ourselves. We got Norton's resistance how much? 24.286. We got Norton's current. Can you draw a current source around this and then resistance, that is the equivalent, Norton's equivalent, then you add the load resistance and find out the load current. So long as you see what is happening here. So, have you done it? Have you done that? What is the answer? What is the answer? So now we have step 1, we have step 2, we are going for step 3, I think we have already done it. So we are at step 3, so it should be, there should be a current source like that, right? This one will be Norton's current. There will be Norton's resistance, there will be AB, and this is your load resistance, right? RL. So we need to find out IL, and IL will be, what is that? IN times RN, okay? Divided by RN plus RL. You agree with me? How do we get that? Quickly, how do we get that? If we have a current here, say for example, the current here was say I. We put I3, say I3, right? So what is the voltage drop here? What is the voltage drop here? I3 times Rn, right? And what is the voltage drop here? RL times RL, right? This should be equal. Yes or no?
Mm-hmm.
So you get one relation like that. I3 by IL is RL by RL. Yes or no?
Yes.
Clear? Now this I3 is what? This I3 is nothing other than IN minus IL. If you apply your KCL here, IL coming here, I3 going there, IL going there. So I3 plus IL should be IL. Yeah? So I3 is IN minus IL, right? Divided by IL. So this is what? IN divided by IL minus 1, right? Yes or no? And then, no, okay. Okay. So you're saying no? Right or not? So then it should be something like IN divided by IL should be 1 plus RL divided by RN. Meaning we can say RN plus RL divided by RN, right? So if we do this one, so it will be IL divided by IN is RN divided by RN. Can you see now? RN plus RL. So what we get? Finally, we get I L equal to IN times RN divided by RN plus RN. Is that? So that formula we wrote here. So this is a kind of a derivation which is what you have done wrong back in your school life. Yeah? Yes or no?
Yes.
So you said no. You said no. So now what would be the value? We can say IL is the answer. What is the value of IL? Someone? 0.118. What is the value of RN? 24.286 divided by Rn is still the same value, 24.286 plus RL was how much? 200, right? So what is this value? Zero point 0.01 is your IL and this is your answer. Clear? Yes or no? This is the answer we got. What you got? Come again? With formula. You are starting on that. Forget it now. Forget it now. Because this is not a part of our business. I just did it. I just wanted to do. It's not the part of the business. You do at home. You parallel concept. Going there, how do you get the division of the currents? You have done it. You have already done it.
20, not 200, sir. RL is 20, not 200, sir.
Aqui na resistência biológica.
Okay, so what we are going to do sometime, this problem, what we have done here, the Norton's theorem, we are going to apply. We are going to apply Theorim, right? And you are going to do it. Okay. Is okay or not? So in that case, we are going to find out open circuit voltage. Right? Can you do that quickly? Okay, so if we solve the same thing by Thevenin's, what we are going to look at. So it is, so the problem was, so we are not going to repeat to find out the resistance, that is 24.26, that will be there, right? So let's apply Thevenin. Thevenin, same problem. So we get R Norton equal to, this is step 1. Step 1, R Norton equal to R Thevenin equal to 24.26. Clear? So this is your step 1. Step 2, we need to find out V Thevenin, right? That is VAB. Let's remember that. So what we are going to do, so now this one is open circuit. This is 10, this is 20, and that one was 50. And the voltage was 8. Okay? Now we need to find out the voltage here. Right? So we are going to find out VAB will be equal to your VThevenin. This is how much. Okay? Now we are going to take one loop here and we are saying this is I1. Okay? And there is no current in the other loop, that is open. Clear? So we are going to write the equation again. So it should be 20 plus 50 as we just did times I1, which is negative. There is no I2. And then plus 10 is 0. So I1 should be 10 divided by 17. 1 by 7 ampere. This is your I1. Right? Now, step 3. Step 3. We need to find out the voltage here. Now we are going to write equation here. So we start from there. Right? This is 0 drop. 0 plus, here is a drop, that is 12. Okay. Let me. So this one is 0 drop, meaning minus 0. There is another drop, that is 20 I1. Right? Yes or no? Now if you go that one, and this one is going to lower to upper higher potential, so this one will be voltage rise. That one is plus V Thevenin, right? Equal to 0. What was I1? Okay, I1 equal. So V Thevenin equal to 20 I1. That is 20 by 7 volt. What is that? 2.857. Now let's go to, was it step 3 or what? Step 1, step 2. So we are still on step 2. Step 3 will come here. So step 3 will be, we'll have VThevenin here, we'll have resistance here, and this will be your load resistance, which is 200. Can you see there? This is A, this is B, and this is VThevenin, right? And this is RThevenin. RThevenin was this one, 24.286, and VThevenin is 2.87. So we get IL. IL will be, so this is your Thevenin's equivalent. IL will be VThevenin divided by RThevenin plus load resistance. VThevenin was how much? 2.857. RThevenin, how much? 24.286. Load resistance was 200. This is apparent, and don't give me different answer. So 2.857 divided by 24.286, 200, 0.01. So the answer we get here, the answer we got there, the same answer. Clear? Yes. So meaning, whatever the problem is given to you, if you solve it in different method, you should get same answer. But there is something happening here. I will show you that the Thevenin's equivalent and Norton's equivalent, they can be their equivalent to each other. Why? This is your Thevenin's equivalent, right?
Yes, sir.
And we had Norton's equivalent here. So this one we got, this is our Norton's equivalent. Clear? And this is the load side. So these two equivalents must be equivalent to each other. If so, what should be the relation between Rn and RThevenin? And what would be the relation between VThevenin and IN? There should be some relation. What is that? You get my point?
Yes, sir.
So if we draw, okay, let's write down the values what we got here. So this is IN, it's same for everything. We got, okay, right? Okay. We are going to say so this one will be source. This one will be source conversion. Before we go there, we are taking the values from the previous example. So we are still at problem 1, right? And we got IN something. We got
current
RN.
current
Right? We got Thevenin. We got VThevenin. Clear? Tell me the values. Tell me the 0 points. I have one that is at 24.286. The same value 24.286. Right? Norton's current was
0.118, sir.
okay, 0.118.
Yes,
right?
sir.
0.118 ampere, and VThevenin we
2.857 volt.
2.8 volt, 2.857.
5, 7.
7.
Yes.
Right? So these are the values we are getting here. These are the values we got there. Okay? Now tell me, do you have a calculator?
Yes, sir.
Okay, fantastic. Can you please multiply IN and RN? IN, Norton's current, multiplied by Norton's resistance, what value you are getting? 2.857. Is it equal to Thevenin's? So then we can say this is one formula. Right? We just got it here. We multiply the two, we got Thevenin. We saying no. We saying no. Go and smoke and come back.
Ivy.
There's the other thing. So you get Thevenin from Norton's equivalent, right? So if you have a Norton's equivalent, in order to get Thevenin's equivalent, you can find out Thevenin, right? And so meaning what we are getting Thevenin equal to IN times RN, and Thevenin equal to RN, meaning on the right side here, we have quantities from Norton, and in the left side here so this one is Norton, this one we get from Norton, this one is from Norton, and we are getting Thevenin's here, meaning we have Norton's equivalent, we can find out the Thevenin's equivalent from there. So we have current source with a resistance, now we can have voltage source with a resistance. Clear? Yes. Meaning we can convert current source to voltage source. Source conversion. That's what I said here. Source conversion. Current source to voltage source. This one. Source conversion. Current source to voltage source and voltage source to current source. So second one, we need to find out. Okay. Tell me. IN is there. So how do you get IN? Can we try to find out Thevenin divided by Thevenin? What is that value? Is it that? So we get this one. Meaning if we have so we can find out IN is Thevenin divided by Thevenin, and we can find out RN equal to Thevenin. Right? So this one we can say this one is current source to voltage source, right? Is it that? Can you say that? Current source to voltage source, right? And this one is voltage source to current source, right? So this is your source conversion. Meaning coming to the theorem now. That theorem we call it source conversion. I saw something. Some of you guys applied source conversion. I don't know where you learned it, but anyway, read it. Some of you already applied source conversion. I saw in the WhatsApp group. Okay. Now, but we did not discuss that one by that time. So if we have a voltage source and resistance like that, this is your voltage source, right? And we have the current source with the resistance here, right? Okay? This is the current source. There is a current. Let's put IN just to make our life easier. This is RN. This is Thevenin, and this is Thevenin. So this is your voltage source. This is your current source. They are equivalent to each other. They are equivalent to each other, and we get the relations there as we got. Okay? That relationship got there. Is it clear? Right, so we are good. This is page 3. This is page 4. So we have learned Theorims, we have learned Nortons, we have learned source conversion. Question? No? Did I have your autograph, all of you? Take it. Okay.
So D as voltage. Baby. Want ik naar het midden. Moeten we mensen aan jullie schrijven erbij? Kan een mensen zijn bij ja. Nee, dat is echt gewoon.
Guys, so now we know much of current law, much of voltage law, mesh analysis, loop analysis, we know Theorim, we know Norton, we know superposition, right? So we are going to before we go there, let's read what is written here. The current which flows in any branch of a network, this one, is the same as that which would flow in that branch if it were connected across a source. This is the source, right? Of electrical energy, the short circuit current of which is equal to the current that would flow in a short circuit here across the branch. So this short circuit current is here, and the internal resistance of which equal to the resistance parallel to the current source current across the open circuit branch of terminals. Meaning this resistance is the open circuit resistance as we got in Thevenin's theorem. Clear?
Yeah.
Norton's theorem, we did it, and this is one example, and you can do it of your own. And here, the second example, there is a current source. Now we need to know what is the difference between current source and voltage source. Ideally, a voltage source does not have any internal resistance, right? And ideally, current source has infinite resistance. Meaning, if you connect any resistance across a current source, there will be no drop of the current. The current source will have constant current. That is constant current source. Again, constant voltage source, the voltage across the battery will remain the same if there is no internal resistance. Clear? But basically both of them are energy source. Both of them are supplying energy. One is in the form of current and the other is in the form of voltage. So that's why you call it voltage source and current source. And current source is drawn like that, and voltage source you know how you draw. Clear?
Yeah.
Okay, and here this direction will show the current will flow in that direction. In the battery you know the plus and minus, and it will come out of plus and it will go in the minus. Clear?
Yeah.
So this is your something new, delta to star and star to delta. You look at that, The left side looks like what? It's nothing other than a delta, right? And the right side is star. So we need to find out the relation between them. Meaning if you have a network, there is a delta, so there are 3 points ABC, you can have equivalent star resistances and you can replace this delta by the star. It will not affect the current going to the loop. So meaning you are asked to solve the current through a load, right? And the circuit is a bit complicated and you cannot find out series parallel combinations, right? Then you will try to find out a star or delta. If you convert that delta to star or vice versa, star to delta, might be you can get series parallel combinations. Then you can solve it, right? So you might be asked to solve a problem using star delta conversion or delta star conversion, right? So this one I'm not going into the derivation, right? But we are going to apply it. Later on, after the class test and semester test, if you guys are interested, we can do it through WhatsApp group. Does it make any sense? Or I'll ask some of you to find it out, and then you are going to give me the derivation. Yeah? Yes. Good. So here you have 3 points ABC, and here also we have 3 points ABC. So this star is to be converted to, this delta converted to star. Meaning we know these resistances. We need to find out that one. So we need to find out RA. How do we find out? That would be, we are going to follow a thumb rule to remember. So if you put it here, right? Now let me do it. If you put it there, how will it look like? So let me tell you the formula first, and then we are going to do it in this overhead projector. So this one is RA. Here we had R2. Here we had R3. Did you see that? Yeah. And here we had R1. So in order to get this one, how do you get it? Product of this one and that one divided by summation of this one, that one, and that one. Product of R2, R3 divided by summation of all. Similarly, so again coming back, if you need to find out this one, product of this one and that one divided by summation of this three. Or this one also product of this and that divided by summation of the three. Yeah? Now if you go back there, if you want to find out this one, how do you get it? This one is this plus that plus product of these two divided by that one. Yeah. Meaning RC plus R.
Alright.
Okay, let's do this one, R1. R1 is RP plus RC plus RP divided by RA, not R1, RA. So I'll do it here to make it a little bit more clear. Okay. Let's take 3 points here. Right? Why the color is not coming? What is happening there?
6 as
Which
out.
one?
Out.
So next, so if we here one, see, that one is say R1, R2, R3, right? And we say this one is R12, R23, R31, right? Now, you remember the thumb rule. Do you? What is R1?
R1, 2 plus
R1, 2,
plus R3, 1.
R1, 2, R3, 1
Times.
divided by R1, 2 plus R2, 3 plus R3, 1. Was it that? Was it that or not? Meaning this resistance is product of these two divided by sum of these three. Clear? Similarly, this resistance is product of these two divided by summation of these three. This resistance is product of these two divided by summation of these three. Now, which two we are going to take? At this point, these two resistances are connected, not that one. So, for this one, product of these two divided by summation of these three. Clear? On the other side, if you need to find out R12, so what is this conversion? Star to delta, delta to star.
Delta star.
This is delta to star. Because this side or delta resistances, we are finding out star resistances, right? And the other one, R12. R12 would be what? R1 plus R2 plus R1 R2 divided by R3. And this one is star to delta. Here, meaning, sorry, we need to see that one as well. Need to see that one as well. So here, R12. R1 is connected here, R2 is connected here. So R12 is this plus that, plus product of these two divided by that one. For this one, this plus that, plus product of these two divided by that one. For this one, this plus that, plus product of these two divided by that one. Clear? Yeah. Now I'll give you one hint which you are going to apply to prove this theorem. And you are going to do it at home. Let's find out. So we are saying proof. We are giving a bit of hint. Okay? Now, in a network, that will be a bit of problem. Let's. For this one, let us draw again. Can you see or not? So 1, 2, 3. These are the nodes. This is R12, R23, R31. This is R1.
Hi.
R3. Okay? Right. Now, these 3 points, 1, 2, and 3, they belong to the same node of a network. Right? These points, whenever we are converting star to delta or delta to star, these 3 nodes, 1, 2, 3, they belong to the 3 nodes of a network, of a big network, right? So we are simplifying that bit. Clear? Now, if we want to find out the resistance between, so if you have the delta, you don't have the star, right? If you have the delta, what is the resistance between 1 and 2? If you have the delta, so you take delta, what is the resistance between 1 and 2? Resistance between, so we find out resistance between 1 and 2. So from the delta point of view, there is no star, delta is there. So there, this one is there, right? And these two are there. Can you find out the series parallel combination? It would be R1, 2 multiplied by R31 plus R23. These two are parallel, divided by R12 plus R23 plus R21. Can you see that? I'm going to draw it here. Say only delta is there, meaning here is one, here is the other one, right? So this is your point 1 and this is your point 2, and here is your other one, that is R12. Can you see? R12, R31 and R23. Meaning point 1, point 2, and this is your point 3. Same circuit, same thing. We just arrange it just like series parallel, right? And then you see R1 is in parallel with the series combination of R31 and R33, right? So we did that one. Clear? Yes. So this is one clue of the hint for that one. If this network is delta. Now if we have star. What we get? Between 1 and 2? Between 1 and 2, what we get? All the star you have, you get what? R1 plus R2. Yes or no? Yes. Meaning you have simply something like that. This is R1, this is R2, and this is R3. Now if you are asked to find out what is the resistance between these two, R1 plus R2, because if you connect, how you do, if you connect a battery here, right? Say you connect a battery here. What will happen? This current will flow through this, no current will be there. Meaning, this battery, say E, if you want to find out the current, since this is E, if you find out the current, would be E divided by R1 plus R2. Meaning the equivalent resistance between these two is R1 plus R2. Clear? Yes. So, these two will be equal. This one and that one will be equal to each other between point 1 and 2. Similarly, you can find out between point 2 and 3, you can find out between 1 and 3. It is solved. You have some relation between R1, R2, R3, and R12, R23, and R31. Then you solve. Right? You might take 2 pages to do it, but you can do that. Any questions? So we have done star delta, but we will see whether we can quickly apply that. If not, we are going to do it at home. There is one more thing, that is maximum power transfer theorem. Maximum power transfer theorem is something like there is a network, right? There is a network here, right? Now you are asked to find out what should be the resistance. If this resistance capital R is variable, what should be the resistance such that the power transferred from this battery to there is maximum. So that is that we call it maximum power transfer theorem. You have a load, you have a circuit. What should be the load resistance such that maximum power can be transferred from the source to that resistance. That one would be maximum power transfer theorem. The answer would be, if you remove that and if you find out internal resistance between these 2 points, as we did for Norton's resistance or Thevenin's resistance. Clear? If we do that, then we can find out the internal resistance of the circuit. Right? Whenever this resistance is equivalent to the internal resistance of the circuit, then the power transfer here will be maximum. That is a theorem. Right? That one also you can quickly prove. So here, this is the network, this is a battery, there is internal resistance here, this is the load, right? Now in order to find out the internal resistance, this bit will be short circuited. You open, what is the resistance here between these two? Small r. So when capital R is equal to small r, then maximum power will be transferred, right? And which can be quickly done mathematically. Can you draw that circuit quickly? Maximum power transfer theorem. Do you have the circuit ready now? Got it? Good, man. So it was there. That is the resistance that is in. So open circuit, internal resistance will be smaller. So theorem says power transfer here, right? If that power transfer here is P will be equal to P max. When R equal to small r. This is your theorem, right? Now let's find out what is power. Power is, if you have a circuit like that, the power should be I square R. Is it that? What is the value of I? I should be equal to E divided by R plus R, right? Meaning P equal to, instead of I you put E square R plus R square times R. Clear? So you get E square R divided by R plus R square, right? So instead of that we can say R square plus R square plus 2 times R times R. Can you say that? Yes. Now what we are going to do, we are saying E square R as it is R square plus R square minus 2RR plus 4 times RR. Can you do that? Yes or no? Yes. So this is E square R divided by R minus R square plus 4 times RR. This is your P. When P will be P max? When the denominator will be minimum, right? When the denominator will be minimum, there is a square term. There is not square term, something like that. There is a square term. This square term, the quantity, whatever might be the value of R and R, the square will always be positive, and the minimum value can be 0. Right? So in order to have P equal to P max, in that case it would be E square R divided by 4 R capital R, because this one, the minimum value is 0. So we are saying 0 plus that one. Does it make sense? Yeah. So this is E square divided by 4 times R. This is your maximum power. So when the internal resistance is equal to the load resistance, you get maximum power. Clear? So this is your maximum power transfer theorem, and we can apply anywhere we like to apply. So that is all about so now go back to okay, so now we are not going to do any example or so, but we are trying to find out something what we learned here. You see this network. Can anyone identify in this network one star? Find out one star in this network. Yes. Do you find out any star? What is that?
A star.
2, 6, 5. This is a star, right?
Yes, sir.
So this star point will be this one, and that one. Yeah? So then we can say this will be a delta.
Yes.
So this star can be converted to a delta. Now can you find out a delta here?
Good at home, sir.
So this is this a delta? Is this a delta? No. Huh? Yes. Is this a delta? Yes. This is 0.1, this is 0.2, and this one is 0.3.
Yes.
Meaning these two resistances you are going to make a V here. This one, that one, right?
Yes, sir.
So this one is a delta, and instead of delta you can find out a star here. Can you?
Yes, sir.
So thus you apply star to delta, delta to star, then your life becomes much easier to solve the problem. You can apply series parallel. Clear?
Yes, sir.
Now going back. Sometimes this one becomes easier. Now tell me, can you find out a delta here? Can you find out a delta here? A, B, C, D. Can you find out a delta? You can find out a delta between A, B, and C. Can't you?
Yes, sir.
Meaning 10 ohm, 30 ohm, and here it is 35.
Yes, sir.
So you have the delta because this point is hanging. So what is there? So then there is a delta and you can convert the delta into star.
Yes, sir. Yes.
It has been seen that most of the time if you convert a delta into star, the calculation becomes much easier. Don't do the other way around. Most of the time if delta is converted to star, life becomes much easier. Right? And here, now you are asked, in this circuit, you are asked what should be the value of this R3, not 10 ohm. What should be the value such that you can get maximum power transfer here? Can you do that, apply maximum power transfer?
Yes,
The
sir.
question is what should be the value of this resistance, which is not given 10, such that the power transfer from here to here will be maximum.
Should be the same as
Meaning
R1.
this resistance should be equivalent to the internal resistance there.
Yes, sir.
So you short circuit that one, open circuit this one, find out the internal resistance.
Yes.
That resistance when you put here, then you will get maximum power.
Yes, sir.
Then you calculate, apply your base analysis, calculate the current there, putting the internal resistance here, and then I square R, you get the maximum power. So
Yes.
this is the situation where you get maximum power transfer and the value of the maximum power.
Yes.
Clear?
Yes, sir.
Any other question? Okay, one thing is left. Somebody asked me someday, there was a problem here. Now I want to ask, what is the problem there? This is a formula. You have one wire, right? So this is your wire, right? This wire has a length. And this one, if it is uniform cross section, it has one cross section. Clear?
Yes, sir.
So length and cross section, and this is made of a material, might be aluminum, might be copper, might be something. Every material has a resistivity. Okay? Meaning different material have different resistance
Yes, sir.
for same length and same cross section. So if that resistivity, okay, let us put it this way. The resistance of that one. This resistance will increase when you increase the length.
Yes, sir.
This resistance will decrease, will be inversely proportional when the cross section is more. Right? So what is here? These are resistance is proportional to L, right? Inversely proportional to area of cross section. Yes or no? Yes. And then, so R is proportional to L divided by A. And there is a proportionality constant, that is rho, that is the resistivity. So resistance equal to resistivity times length divided by area. Area will be meter square. Remember, length will be meter. And resistance is ohm. Then you can find out the resistivity. What is that one? Ohm per
meter. Scope.
ohm meter. Is it ohm meter?
Yes.
It should be ohm meter. So you know that.
Yes, sir.
So now, if you are given the values in this formula, if you have all the values except one, you can find out. Right? Now you are asked the length is doubled. What will happen to the resistance? The cross section is doubled. What will happen to the resistance? You can do that,
Resistivity.
right? So there is no more question. We are done, sorted out. So syllabus is complete, but next week there will be some more examples done here. But you will have your responsibility to solve problems of Faraja and the other book and wherever you get it, right? And if you go to YouTube and try to follow a lecture by some Indian lecturer or whatever, don't be confused. There might be something you do not like it. Try to compare what he did here, right? And as you, we did right thing, right? Thank you.
Bye.